Cek. Kursi depan diisi dulu ya. Kalau udah siap ini profnya diajak ke atas. Sudah siap di lantai 2 sejak tadi soalnya. Itu yang paling depan belum terisi semua. 1, 2, 3, 4, 5 itu masih kosong. Yang depan sini 1, 2, 3, 4. Silakan diisi dulu yang depan. Kursi yang depan paling depan diisi dulu, baru yang belakang-belakang.
Bunis, nggak
Silakan.
apa-apa. Nggak apa-apa Bunis, ada yang baru datang. Saya suruh ke depan ya.
Cek.
Cek, cek, 1.
Cek.
Tes, tes.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Welcome back to the afternoon session of the Visiting Top Professor Program, Faculty Mathematics and Natural Sciences, Universitas Negeri Surabaya.
We hope everyone had a pleasant lunch break. So this afternoon we will continue our academic program with General Lecture 4 entitled Teaching Science for Sustainability, the Role of Mathematical Modeling in SDGs. This session will discuss how mathematical modeling can support science teaching and learning, especially in relation to sustainability issues and the Sustainable Development Goals.
Before we begin, we kindly ask all participants to switch their mobile phone to silent mode and to actively participate in this today's session. It is our great honor to welcome our distinguished speaker, Professor Ebenezer Bonyah, M.Ed, M.Sc, Ph.D. To Professor Ebenezer Bonyah, we respectfully invite you to deliver the lecture. The floor is yours.
Thank you very much for the warm reception. Good afternoon, students. So I bring you greetings from Ghana. I'm sure most of you haven't heard Ghana before. Ghana is one of the countries in Africa. So I don't know the background of most of you sitting here, but I'm sure all of you are in this faculty. So today's afternoon lecture, I'm going to talk about teaching science for sustainability, the role of mathematical modeling in the SDGs. The SDGs are standard KPIs that United Nations expects every country to meet. So I'm saying here that the global sustainability crisis, what are the issues? One of the issues has to do with climate change. You see global warming, very hot. But 50, 20 years ago, maybe Indonesia was not hot like this. Since I came, I've been informed that it used not to be raining like this at this time, but now it's raining. Water pollution. Somebody was even telling me a story about the sea over here. The taste of the fish in the sea is not too delicious compared to other part remote sea due to pollution. Food insecurity. Now in some most places food are very scarce, very expensive compared to those days. Then biodiversity loss. Here we're talking about the natural ecosystem, totally gone. Then urban congestion. In my university those days, we had only 2 people sleeping in one room when I was a student, then about 30 years ago. Now, same room has not changed. We are putting 4 students in the same room. Due to what? Urban congestion. There are so many students going to school. Everybody is going to university. Who is staying home? Nobody. And government doesn't have money to meet the industrial needs, the societal needs, sorry. And therefore, sometimes you need to do what you can and let the system work. So, the main idea behind modeling, basically, mathematical modeling, basically is to do prediction, optimization, simulation, forecasting, decision making. So if I have a core equation, let's say y is equal to f of x plus a certain error, then the question is what can be modeled, what cannot be modeled, cannot be what? Predicted. It simply means that if you don't have a model, it means you cannot what? Predict. So we use model to forecast or to give what? Prediction. I'm sure some of you are from the natural sciences, right? Some of you are also from, is that chemistry people here? All of you are from natural science? Okay. The natural sciences is still, we'll be dealing with some bit of biology, so and so forth. And what we're saying here is that model are the end product of processes that we go through. I didn't say mathematical, I said modeling. So we go through to develop a certain product where we can predict the outcome or the future trend of such products. And we say mathematical model because we are using mathematics to combine or to interact with different entities or different variables to produce a product which we can predict what's likely to happen in the future. For example, a woman preparing soup. In my country, if you are preparing soup, you need tomato, maybe some vegetables, onion. These are variables you need to prepare. So the combination of these vegetables to produce a soup, so that the soup now become like a model, which you can use to predict what will happen if, for example, if you put more salt, what will happen? Or if you put more tomatoes, what will happen in the soup? Or if you put more onion, or if you put less onion, and so and so. So that is how you should picture a model. Exactly. So it's very simple. So we're saying that the end product, like a soup that you have, we can leverage on that product to give a prediction or to what? To make a decision or to give us information about the likelihood of what will happen in future that we are not there. And this afternoon, in the morning session, I did make mention of a scenario like airport. I have not gone to Jakarta, but I know the airport may be very busy airport. So maybe if the government decides that in the next 20 years, what to be the state of that airport? If they are getting a lot of people coming to Indonesia or a lot of people living in the airport here, it means you have to plan such that the next 4 or 5 years, you can meet the demand of travelers using the airport. The question is, will they require building a new airport, or will they require to expand the existing infrastructure in the airport? And this decision can be known or can be taken through modeling. Once you have the right process together, you can use mathematics as a catalyst to combine these variables. And when you get this combination through mathematical rules, principles, formulas, whatever it is, then you solve this mathematical problem. The solution then obtained, you interpret it realistically, what they mean in a rare sense. So yesterday, for example, I talk about multi-interdisciplinary. So I said that there's no single discipline like natural science that can solve a particular problem that you face or we face in the society. Let's look at smart road. I saw so many motorbike since I came here in the morning. So many of them. The question is it good to have so many motorbike? Some of them are not even good drivers of the motorbike. It can easily cause accident. They can be killed and so forth. So this is a problem that needs to be solved in future as far as DCT is concerned. We can use mathematical model to get an idea about the nature of the problem where and what should be likely to be done. In this context, for example, you require so many disciplines because we are talking about road. Who constructs road? Civil engineers, especially those specializes in transportation aspect. We also need somebody in planning who have studied planning, who's a different discipline, especially urban planning officers. You need a sociologist to talk to people who sit by the road. Because we are expanding the road, we are going to destroy people's home. So they need to study all dynamics. You may even need an ecologist or environmental scientist because sometimes constructing the road, you are going to destroy ecosystem. So you see one problem, it is showing that you need several entities which now come to be a variable. And you combine this based on the experiences expert will share. Will determine how you combine these variables to come out of a model. And then when you solve this model mathematically, then the solution can now be interpreted, which we can use to advise policymakers to take the right decision. So basically, this is the whole concept about the modeling thing. And that's, for me, we should be thinking about it. So now we're looking at the SDGs as a complex network. We're looking about food affect climate, because if you are cutting more trees to plant food crops, climate will be affected. Climate can also affect food. If the climate is not good, whatever you grow, they won't do well if you are not using irrigation system. Or if you are even using irrigation, what about temperature? What about humidity? Can you control? You can't control. Water affects what? Health. Is that not it? Poor water can affect if you take in water which is contaminated. You see the consequence. Energy affects what? Economy. If you have industrial plant and everybody uses phone, so the company that manufacture phone, there are no light energy for them. How are they going to work this phone? Cities affect what? Ecosystem. You have natural environment, you have to cut and rebuild them, and so on and so forth. So here the key message: sustainability problem are interconnected dynamic system. So sustainability, how to sustain a system we live. You see that the road example I give is connecting so many entities. You have to bring in so many entities that are interconnected. So the question is, what is mathematical modeling? Here I said that mathematical model is a simplified representation of reality. So how you conceptualize a knowledge or idea which mimic or depict what? Reality. But in some advanced country, when there's a crime, maybe somebody kills, shoot, or this or does something, normally this is what they do. Maybe you may be sitting here, somebody passes, consciously or unconsciously, you appear to have looked at the person's face, but because the person knows your friend, The person may be the first time you are seeing, so you are not even try to see the person's face and capture into your memory. But if you see the person, sometimes that's so. If you see the person, can you identify? Say, yes, I saw the person. If I see the person, as soon as you see the face, the memory scans to tell you that it was this gentleman or this lady who passed. So in advanced system, they invite an artist. So you describe the face, the artist can use the description to mimic the face that you saw. They can use that face, the description, to trace or even scan in the computer and trace if anybody image in the system is similar to the face they are seeing. That is the principle of mathematical model we are talking about. Trying to represent something conceived to mimic the reality of that thing that we have conceived. And that is mathematical model. We're saying that it is used to understand a system. Maybe in the natural science department, some of you are doing biology courses, isn't it? Do you take courses in biology? The natural science department, what do you people study? What's your background?
What is your study program? Science education?
Natural science. I agree.
Natural
So
science.
the natural science, what is in the natural science? What do you study there? Yeah, that's all. Natural science, in my sense, in my country, we call it integrated science. So we have integrated the physical science as one entity, which people call the natural sciences, right? So in the natural science, there's a bit of physics, a bit of chemistry, a bit of biology, right? And agric. Yeah, because agricultural science also some part could be natural science and so and so. Yeah. So that's exactly what I'm trying to see. So in biology, for example, we are looking at germination, how plant germinates or flowering, so whatever it is. We can model. We can study the characteristics of a plant, the nutrition, or it could be animal, reproductive system of an animal, anything. If it's like this, a plant, if you have two plants, same plant, but they are growing in different places. One of the factors, for example, that would let maybe one plant be flying well could be nutrition. If one plant receives better nutrition than the other one, if one plant, the climatic condition is better than the other one, definitely the one receiving better nutrition, better climate condition will fly better than the other one. Is that not it? So these factors are things that should be form part of what your model. And in the modeling too, one very important thing you must also bear in mind: assumptions. Assumptions. Let's take, for example, in a class. Sometimes some students are better than others. The reason could be that the person naturally are good. Naturally, Allah gifted the person high intelligent quotient. We agree. It could also be that in some situation, some students are highly disadvantaged. One, getting food to eat is a problem. Even as in the person in school, when you call back home, always parents are complaining even what to eat. It could be possible that you usually have students in school, they are battling with sickness, and how the person gets the state of good mind to learn. So if you even saying that somebody is not doing well, the person not doing well may be due to somewhat factors. So in your modeling, some factors must be held constant. That let's assume that everybody get food to eat. That become what? An assumption. We can assume that, let's say, everybody in school has gone through secondary, senior high school. So he understands some basic physics, chemistry, biology at the secondary school. We can assume that. We assume that, for example, that everybody in this school attends lectures. Because if you don't attend lectures, how do you learn? So you give these things that I've said in terms of how we learn as what? Assumptions. We are keeping them constant so that they do not affect what? The model that we develop. Otherwise, if you develop any model without credible assumption, anybody can flaw your model. I will ask you, okay, you have developed a model on difficulties in learning natural science. We agree. Okay, now just come and say that if in your model you did not assume that everybody attends it, I will ask you, okay, assume that these students you claim about learning difficult, it is due to the fact that they don't attend lectures. Then the model is collapsed. It doesn't make sense again. So we make right assumption based on what? Reality. So that any prediction that we use the model to make, it will make sense in the real realm of life. I hope it's clear. So we can also use model to optimize decision, maybe to make things to take a decision which optimizes something that benefits society. We can also use to guide policy, because if you predict, the predictions can lead to guide policymakers so that what you have predicted doesn't happen if it's negative, and so on and so forth. So in the modeling process, we say that reality, what problem that we have identified in a real life. Then you make assumptions like what I was talking about. Okay, this must remain constant, this should be this should be that, should be that. Then you transform the variables that should be part of your model. Some of the variables must interact. For example, if you talk about diseases, you are doing biology. COVID. When COVID came, you saw everybody wearing nose masks. Anywhere you go, people were washing their hands. So people were very cautious about basic hygiene so they did not get COVID. Even COVID time, I'm sure you will not be allowed to sit like this, isn't it? So in a modern COVID infection, for example, we would have taken into consideration that for people to get infection, people must mix together. If you don't mix, how do you get COVID? That is one mode of transmission. So we say that the population are mixed together. Mixed together, maybe we can do things together, we can eat together, we can sleep together. So if one person has the disease, by the time we realize it can affect half of the population. Are you getting the principle? So how do you also know this? How do you know what I'm telling you? You have to consult experts. So in doing one aspect of your discipline, you may end up consulting other discipline to get the right things done. I don't know whether in this slide in the morning we show a slide where even if you want to model a disease, how maybe you get donkey fever and so on and so forth. I am mathematician. I'm not medical person. I must consult a medical officer or a biologist or health practitioner to tell me more about how somebody gets COVID. So based on this description, I could further consult literature, what papers people have written saying about it. After that, I will move to expert modeler, which is a mathematician. How do we now communicate what the experts say in terms of mathematics language? Once we're able to convert this into mathematical language, let's say equations, then the next thing, I use mathematical principles to solve these equations. So the solution that I obtain I must interpret it in the context of health practitioners' principle. And they will say that if maybe S is 5, it means that maybe the rate, maybe let me use the right term, the reproductive number, which indicate the number of times an infectious person can infect others in the virgin population. So if I calculate and then I get reproductive number to be a certain value, then I can explain it to, or I can interpret it to mean that in the virgin population, if one person get COVID within, let's say, a day, it can cause maybe 8 or 10 people to have COVID. That is the interpretation. And so what we do after the interpretation comes after you do your simulation. The simulation is the putting data into the maybe the equations or the parameter values and using a software, maybe MATLAB, whatever it is, to get graphs out of what we have done. So we interpret the graphs to mean a practical interpretation of reality. And that's exactly what ought to be done, or what is done. Then somebody call let's say a decision maker here, maybe Ministry of Health. They are in charge of health of people. Then they will look at their results and guide them to take a decision. So for example, they can write to the vice chancellor of this university that this is the study that have been done, and looking at it, they may be advising that because of what these people are saying, schools should be closed or should not be reopened at this time, so that they take proper measures. And so that's what model does. It's very interesting, very practical, very good in making sense of mathematics. So basically, types of sustainability model. We look at optimization model, use of resources allocation. Here, the focus is how do we optimize resources. I'm told that this faculty has 23 programs. That's what I heard in this faculty. So many. So if the dean has money, we want to buy maybe computers or tables and chairs to this department. Which of them does he have to give them more? Then that we use optimization techniques, not the way the dean thinks, but we use scientific means to based on available number of students in each program. We use mathematical model to predict which of them should have more, resources than others, and so on and so forth. There also are what dynamic models used for system change over time. For example, the disease I talk about, we use dynamic model to, if time t is 5 o'clock now, what will happen when time is maybe the next 2 days, and so on and so forth. Then we also have agent-based model used for human and social behavior. Here, if you want to check behavior dynamics of human being or animals, we can model using agent-based model to predict what's likely to happen. So that is types of sustainability models. So, for example, we have population and resources dynamics, logistic growth. So I have the rate of change of N over T, which is R, multiplied by N bracket 1 minus N over K. The N is the total appropriation of the resources. Maybe the resources could be a number of computers the faculty has or want to buy or have bought, or the number of students. Then the growth rate, the rate at which students are being admitted at the faculty or each department. Then carrying capacity, how many students can the faculty contain? These are basic data, so we can put these values in this equation and then we can use it to do the prediction. So easy. So this one may not even to do dynamical solution. Once you have this value, we can put this manually, even do this calculation even on our phone to determine how, how with time the faculty can grow in terms of numbers or in terms of resources and so on and so forth. So the growth cannot continue forever in finite term. In other words, this faculty number cannot grow to certain. At a point in time, it will begin to decline. It is impossible that the program they are running here, if they don't change them well, people may not be too much interested in what is existing. That is why I'm sure with time they try to bring in new programs. Now I'm told they are doing data science, artificial intelligence, and so on and so forth, which used not to be part of the faculty so many years ago. Another one is called this. Says here, let's look at SDG2. SDG2 says that 0 what hunger. Nobody should go what hunger. But are we not in this world where people don't get food to eat 1 week, 2 weeks, 3 weeks, which is possible? Because if you are saying we should not go hunger, we agree. But does the society give food free? Do we have free food in your country where if I don't have money, I can go to a shop, they will give me food to go and eat? In my country, we don't have that system, but here I don't know. Maybe you have it. So we can use application of modeling to check this crop yield prediction, look at irrigation optimization, soil facility analysis, food supply forecast. So we can look at these entities to model to see or something related to the zero free food, whether it's actually being realized. We say that the message this is carrying is mathematical model, improve food security. So zero food, which is SDG2, we can model to check how we are getting to zero food, meaning everybody get food on this planet, irrespective of where we find yourself. So you can link it to SDG2. Now, for SDG6, we call clean water. SDG6 says that everybody on this planet must get clean water. But you go and see the kind of water in some places, animal and human being are drinking from the same source of water. In my country, for example, a lot of people have destroyed the water bodies we have to search for gold. But they want to be rich. They don't care about what happened to others. So we can model something around water using what we call diffusion equation. You are not in mass, but we can use diffusion equation to model something around water. So here, river pollution, ocean contamination tracking system, water quality management. So the key inside here, pollution spread mathematically, not randomly. So we can model how pollution are being spread in the water bodies that we have. I even told that the sea in this particular town is highly polluted. Right, so we can use this equation to model how, because when you get the data, you can easily compute this in. Now we also look at SDG 13, which is climate change. And climate change is something affecting everybody. Everybody is being affected by climate change. So climate change feedback system, you can use the equation I have over here, which T is the new climate. So old climate plus F of beta. What the key idea around this? Positive feedback loop, temperature amplification, nonlinear climate system. And what the key message here, small change can create global consequence. If a global temperature changes even 1 degree, the way flooding will occur on this planet, most people will not survive. Just 1 degree change in temperature in Europe, there will be disaster. Because if you go to Iceland and then some part of Russia, there are some places, for example, Alaska. Alaska is always ice. Even in Norway, there are some places in Norway from January to December, every place is totally ice. They don't use fridge and those things, air conditioning in those places. So if there's a change in temperature 1 degree there, it means ice will be what? Melting. If the ice melt, what will happen? Flood and so on and so forth. So we can connect mathematical modeling to study how human behavior is increasing temperature Allah gave to man maybe 200-300 years ago, which we are destroying them. Then palm oil dilemma. Sustainability optimization. You can use L is equal to P minus lambda bracket O minus O min to also model this. Then they discuss how do we maximize economic development while protecting biodiversity. Then the key message is sustainability is an optimization problem. So if you want to look at sustainability, how we can sustain it, means how can we optimize maybe a small resource that we have to get better output. So basically, sustainability deal with what? Optimization problem. Using small resources to get the best out of it. So we can use this also to model. Then epidemiology. Remember I talked about disease. So the first equation could be susceptible. Susceptible means individuals in the community or maybe sitting here who do not have COVID now. Then the second one, the IDT, the I refer to those who are infectious, they have COVID. They can infect those who don't have it. Then the RDT refers to a compartment, those who got COVID, but they have been treated and recovered from COVID. So application, COVID, you can use this simple model to forecast COVID spread. You can use this simple model to provide the relevant information for Health Directorate or Ministry of Health to give interventions that will prevent the spread of COVID. You can even use this strategy also to provide vaccination principles. When COVID came, most people got vaccinated, isn't it? So that when you get vaccination, it improves your immune system. So that when COVID virus gets in touch with you, you can still survive. Sometimes you fall sick, all right, but you will not die. Okay. So fisheries sustainability. How do we sustain fish from the seas, from rivers? There are some places all the fish in these natural bodies have been depleted. Man has consumed all of them. But these fishes must be sustained so that generation unborn can still have access to these resources. So we can use safer fishery model. It's a model, the equation is a model. Once we fill this equation with the right values, we can use it to predict. So the variable F refers to fish population. So maybe you go to a particular river, if you can use a certain artificial, maybe this artificial intelligence is available to count the number of fish in the river. You can use a system to determine the number of species in the river or the sea, whatever it is. The E is fishing effort. How we are putting effort to catch fishes, that effort. Then K is the catchability coefficient, how they are able to catch. So once we have all these values be fit into the equation, what is the model? We can use it to predict. So overfishing can mathematically collapse ecosystem. So if I calculate this model and then the value says that it is interpreted with overfishing, then it means the ecosystem can collapse. So in some countries like Ghana, some months we don't allow anybody to fish from the sea, because that is the time most of the fish are actually breeding. So you catch them, it means you won't get fingerling, which also grow to become fish and so on and so forth. Now, traffic flow modeling. You see, everybody realize traffic's around. Here, we can use Begel's equation as a model. So, with the right parameters, you feed in, you can calculate how traffic volumes are at any given time. But what I've shown is PD, partial differential equation, which may be not a volcano ash modeling. If you have heard volcano, and in Indonesia, sometime there are some bit of volcanic eruption in some part of Indonesia. I've been reading about it. So we can use advancing diffusion equation to study how these volcanic, when they erupt, how high they go, and so on and so forth, by feeding with the right data. These are models. So classroom simulation activity. The chocolate sustainability game. Rules. Begin with 100 chocolates. Student consume resources. Remaining resources regenerate. Learning outcome. Resources depletion. Sustainability threshold. Tragedy of what? The common. So if we have maybe 100 chocolates, then maybe we are supposed to eat 30. Maybe there will be another class that we are supposed to give part of the chocolate. Then the first class eats maybe 90. Then when the next class comes, there's no sustainability because we've gone beyond the threshold. And therefore, even the next class comes, they will get 0. And so on and so forth. So that is the basic principle. Maybe, is it time? It's time. Oh, okay. Oh, then we didn't do far. I was supposed to have 1 hour, right?
But it's okay if you want to finish the presentation.
I can't finish all.
first.
There are many. Maybe. Oh.
Professor, that's okay because we still have maybe 15 minutes more for this presentation.
Okay, maybe let me go through a few of them and you stop. No, I can't do all of them. Okay, so I'll be a bit faster to go through just 1 or 2, then I can conclude. After all, what is important is the principles. Okay, so we said that he said that free tools for modeling. What are the tools that you can use to do some of these modeling things you want to do? We talk of Python. You do physics. I don't know, do you do little programming in the natural science? You don't do, okay. You can use R, NetLogo, Python notebook. Then this software we can apply in solving OD, PDs, agent-based modeling, scientific visualization. I'm sure you do plot some graphs to when you go to the lab to do some experiment, right? Don't you do experiment in the lab? You collect data. For natural science, you should be collecting data, isn't it? So the interdisciplinary science, the SGD modeling clinic team members, mathematics. So maybe you have identified a problem in the community, maybe the university, particular problem. Then you realize that the problem is interdisciplinary. Maybe you need somebody from mathematics background, somebody from biology, from economics, from computer science. You put the team together because no single discipline or study program can solve realistic problem. Sometimes you see that this problem is only about natural science. No. When you go deeper, you see maybe you may need maybe a computer science person, you may need other discipline person to help deal with the problem decisively. So the key inside sustainability solution require what? Interdisciplinary what? Collaboration. Very, very important. So this Monte Carlo simulation, family thinking, then ethics of equations, this one, data challenges. We use Bayesian modeling, which is based on probability. So curriculum reforms, modeling for sustainability development topics, differential equation, system thinking, simulation, sustainability, analytic, policy modeling. So these could be reformed that can come into your curriculum, even though you are doing natural science, but you can have maybe a core course for all level 200, which deal with how to do interdisciplinary modeling, so that everybody will have some basic understanding, so that if there's a real life problem which a company employs you, you know how to connect with other discipline, model it, provide the right policy advice to the company. Also, I saw the content Rongon model, then sustainability flood maintenance in Jakarta, modeling idea. So each of them I try to bring equations, sustainability solution through modeling, policy application, connecting. I did all these things. Maybe we can look at mathematical modeling for air pollution in Surabaya. Maybe this could be the last, then I stop. So what is the problem? Industrial emission and vehicle smoke increase air pollution in Surabaya. Look at even the motorbikes I have been seeing. They are all polluting the environment, including cars. So this affects human health, isn't it? The smoke will affect your health. Climate, the smoke also not only human being, the plants, the living organism, they affect them. Then environmental quality. There are people, especially if they have asthma, they can easily die if they don't have their inhalers around. They can easily die. So this is the last thing that you close. So what is the idea? Then I'm looking at the variable of pollution concentration, how the pollution is being concentrated. Also look at the emission rate, how they emit. Then you look at the natural removal, the rate at which the pollution leaves when they get to that particular place. How did they go? Maybe if it rain, the pollution will be, or maybe they can disperse in air, spread somewhere, but it will take time. So, based on what I've shown to you, I developed this equation, dPdt. Remember, I've shown you what E stands for. E is emission rate, right? What P stands for? P stands for pollution concentration. Then K is a parameter, which is the natural removal rate. So once I get these values and put into the model, then the outcome of this solution can be used to what? Give a prediction what is likely to happen in the next 3 days, 4 days, 1 year, and so on and so forth. So that is the modeling process. And therefore, they can be what? Sustainability around this. Because now we know what caused what. So for example, if cleaner fuel is used, industry reduce emission, public transport improve, then what happened? Then pollution will reduce. But if other way around, we are increasing all of it, what will happen? So these are scenarios that you provide in your graphs. Then what do they connect the SDGs? Based on only on this, SDGs still talk about health. So pollution will affect health. SDG 11 talk about sustainability. Also affects sustainability. SDG 13 talk about climate action. What should we do about climate? So this is a typical problem and the solution. I have another one also on solar, but it's time. So maybe I will not bother you anymore. But I'm here to answer questions, suggestions about what I've presented. So thank you, because I can't finish. There are a lot of them, but at least I've shown a typical example to see. Or if you like, give me 1 minute. I think the other one I reduce it. Okay, so this one, solar energy optimization. How do you optimize solar energy maybe in the school? We are doing some bit of phases. So the problem, increasing energy demand requires sustainable what? Alternative. Because if you are using what you call fossil to produce energy, very costly. Now there's a war in Iran. So for example, the cost of crude is going higher and higher, which will affect the price of electricity we use. So we can use this model. E is equal to eta AI. The eta AI, these are parameters which I didn't put here because we are not in the math system. But it's a model that I have all this data I feed. You can give him idea about the solar energy. And this will have a relationship with what? SDG 7, SDG what? 13. So I think it's okay. This is also about sustainability learning system, learning. So low motivation and ineffective teaching reduce what? Learning what? Outcome. Then I use this model, DL, DT, M of T minus DL, all the value and the variables, you know them. Then what occasion in terms of sustainability, innovative STEM teaching improve long-term educational quality. And does it have relationship with SDG? SDG 4, 9, and what? 10. So that is the connections. So I would like to end from here, then pause. So I'm done.
Thank you very much for Professor Ebenezer Bonyah for the insightful and meaningful lecture. Ladies and gentlemen, we have gained valuable perspective on the role of mathematical modeling in teaching science for sustainability. The lecture has also The lecture has also shown us how science education can contribute to the achievement of the Sustainable Development Goals. And now, we will continue to the next session, namely case-based discussion and question and answer session.
Okay, dear students. Okay, so now we will continue to these sessions. So in this session, participants are invited to ask questions, share ideas, or respond to the cases presented during the lecture. For those who would like to ask a questions, please raise your hand. And you can also ask in Bahasa, and we will translate it for you. So it's mean that now we continue to the Q&A sessions. Ada yang mau bertanya? Okay, the first person who want ask. And please kindly mention your name and study program before delivering your questions. Ya, menyebutkan nama dan program studinya. Okay, please.
Okay, thank you for opportunity. Professor, allow me to introduce myself. My name is Sophie Jana. You can call me Sophie. I'm from class 25 of PFA. Okay. I'd like to ask, how does the mathematics teaching method implement at Akenten Appiah-Menka University of Skill Training and Entrepreneurial Development helps students understanding mathematical concept more effectively. Thank you.
Okay, you asked how my university, the students there are doing well in math. Is that the question? Please, can you repeat the question? In fact, I was trying to see if I can charge my laptop.
Okay, Prof. I'd like to ask, how does the mathematics teaching method implement at Akenten Appiah-Menka University of Skills Training and Entrepreneurial Development?
Okay, okay, I get it. So, my university is a teaching university. In Ghana, universities have been grouped into the traditional university, like two. There are 6 of them that focuses the teaching of pre-service teachers to the pre-tertiary education architecture. And the kind of teaching method that we use to teach our students, because we have prepared them to be a